All right,
Well,
we good to start?
I'm good.
yeah, we're good. So,
All right.
all right.
Let's go.
So, hello everyone. I'm David, Logan, and Elijah will be presenting today. How artificial intelligence is used in targeting marketing.
Oops. All right. So what are the current problems with AI as is? So the privacy of consumer is a huge problem right now because the majority of information that AIs are able to gather is without the person knowing it was collected. So there isn't a whole lot of consent of the data being taking place. There are also third-party businesses that the business-only venture is selling people's personal data to companies. It would be better to have a more streamlined process than having a whole business set aside built for it. Also, it is hard to make the AI's targeting more efficient without using people's sensitive data because the more personal the data is, the more accurately they are able to recommend something to somebody. Also, in order for AIs to learn and improve at advertising, they need huge amounts of data to run through. This would allow the AI to even better recommend ads because it would be able to fine tune the algorithm.
The objective for our project is to inform about how AI is used in targeted advertisement. Our objective has been split into 3 sections. The first section covers the different kinds of AI algorithms, their pros and cons, and which ones are best suited for the different tasks involved in targeted advertising. The second section is how the AI leverages the data to present products and services to potential customers. And the third section is how companies monetize these AI algorithms in different ways.
So, how are AIs and algorithms used, right? Like, what are they, and how does AI use algorithms to parse through this data so companies are able to use it? So right now there's 2 current big algorithms out there. One's open source, which is Hadoop, and the other one is used by Google primarily. It's called MapReduce. What they essentially do is they create little clusters of data. They get big, large subsets of data, and then they make them smaller, and then parse them through more algorithms, right? But what are the goals of some of these algorithms? Like, what do we want to accomplish with machine learning and algorithm implementation? We want to be able to structure data. We want to be able to get large subsets of billions of information from people, like keystrokes, Google searches, purchasing patterns, et cetera, et cetera. That needs to be able to be structured in a way where companies can use that data for being able to profit off of it. Correct. Another big thing that these algorithms need to do is velocity. We need to be able to transfer data between servers extremely fast. Imagine someone in Europe wants to. There's a company here in America and in Europe. Someone maybe like searches something on Google, right? You need to be able to reach that data fast, so you can get the advertisement as quick as possible. I don't know if you guys ever seen, maybe you're searching something, and then next thing you know, on your Instagram, there's an advertisement almost right away. This is what I mean by velocity. It's extremely fast how these things happen. So what are some limitations of big data and algorithms that parse through such data? Well, there's very few algorithms out there. As you saw on the previous slide, there's only 2 algorithms out there. The reason is there's so little because to be able to program something like this, it's not as easy as just learning JavaScript or simple languages that do front-end stuff. This is extremely PhD intensive, very academia research. These algorithms are extremely hard, creating neural networks. So it's just not a lot of development. You maybe be able to, but most people can just pick it up and learn how to code it. So it's a very hard. So there's very few and there's very low third-party development. Another big issue is AI machine learning is usually it's implemented in a single machine. I don't know if you guys have ever seen the algorithm that teaches the car how to go through a path the quickest way possible. It's the thousands of iterations of how machine learning happens. You need to be able to program something to do it over and over again. So then it knows how to do it the next 10,001 time. So this is only done in a single machine. We need to be able to scale this up into thousands and thousands and millions of machines out there. To the cloud, there's billions of users of the internet right now. About half the world uses the internet now. So you're able to parse through all that data in several systems not just one comparison. This is a big limitation. Another big thing is dirty data. How does the algorithm know what's a good search for its intended purposes from a bad one? For example, I'm trying to buy a car. I'm looking up brands, Toyota, Lexus, whatever the case may be. But then I do another search engine that might be like clothes. I look for shorts, maybe a t-shirt. How does the AI know that the algorithm, like the thing I'm searching for, is good for its purpose, right? Like, how does it know how to differentiate from the search of the shorts or the pants from the search of Toyota and Camry, right? So one would be considered good data and one would be considered bad data or dirty data for the specific use. Another big issue is the mediums we use to actually like put in and input things, right? For example, the large consensus is like, search engines, text files, I don't know. But like now we're using videos and audio files. So just think about an audio file, right? You need to be able to parse the keywords. You need to be able to do some sort of audio recognition. So that it makes the algorithm even more complex. But then think about a video, right? You need to be able to parse the pixels. You need to be able to compare it to other pictures on the internet. You need to be able to do so many different things. So the further you go into the mediums, the harder it is to implement these things. It just exponentially gets harder and harder. So these are some of the limitations we're having.
So how do companies use these AI algorithms to target specific individuals? It's a two-step process. The first step is analyzing the data, and that's where an AI parses through both structured and unstructured data to learn about specific traits of an individual, such as personality, mood, habits, and preferences. The second step is leveraging the data. This is used to make the algorithm more specific and efficient for an individual's taste. It uses what's called a feeling AI that parses through data to tailor the products and services to an individual, as well as how and when it is presented to the individual. For analyzing the data, we use a mechanical AI and a thinking AI. Mechanical AI analyzes data that's already been structured and is ready for analysis, ready for analysis by a computer. And what's called a thinking AI analyzes unstructured data. So what is structured and unstructured data? Structured data is data that has already been formatted for easy analysis, typically involves demographics, transaction records, and search history. Unstructured data is data that is usually chaotic, unformatted, and made for humans to interpret. So we have to build computers to interpret it. And this is where deep learning and neural networks are very important. And a 2017 study showed that 80% of all user data makes up unstructured data and only 20% is structured data. On the next slide, we have leveraging data. And this is done by what's called a feeling AI. And they're designed for a two-way interaction between humans and AI. It can measure, simulate, and respond to human emotions, desires, and speech. It deals with the more psychological aspect of human information. And because of that, it can create a psychological barrier between the communication of the AI and the human. That's it for this section.
All right. So now how exactly do companies use this info that is gathered by these algorithms and parsed through by said AI to then monetize to specific consumers? So one way is that Google actually produces profiles and secondary data products that are packaged and sold to advertisers as behavioral futures. Now, what this allows is a company is then able to directly market to the subjects they believe are most susceptible, thus making the marketing process exponentially more efficient. Also, there are third-party advertising technology companies that use AI to tailor advertisements to target particular users for particular contexts. An example of this would be if someone goes to the gym and they visit this gym website often, then their feed will then begin receiving ads that deal with like gym equipment or gym clothes. Also, nowadays our phones are a humongous way that we see a lot of our advertising. Now, most mobile apps nowadays contain something called an ad library. Now, what this entails is it enables targeted or behavioral mobile advertising to like a wide range of audiences. So they're able to cover the different types of people that would be using these specific applications. Also, there's something called native advertising. Now, what this is the concept of creating ads that are so cohesive with the page content. They are assimilated into design and consistent with the platform behavior. The viewer almost feels like the ad belongs there. It's so integral into the layout of the website. It looks like they could be sponsored by said product, thus making consumers more, potential to click on it. Moving forward, our schedule for our project, week 1, begin research, then get into writing our rough draft and our research paper, start working on our presentation, getting working the kinks out, put our finishing touches on it, begin practicing so that the final week we are able to present and finish our research paper. The main focus points and how we're going to split up the work is that David does a specific research on how, the technology behind how the AI works and the new innovations that are coming with that. Elijah will be taking care of the algorithms, used to target specific people and what ways we can improve on it. And I will be researching on how exactly businesses use and acquire this data to then monetize their products. So overall, we plan on giving a full insight on how exactly AI is used in the process of targeted marketing and how we can implement the new technologies and innovations to complement the current problems that are in the process. And these were the references we used. Thank you.
Do we do questions like right after our presentation or after everyone's done?
I think after your presentation.
Yeah, I believe it's
Yeah.
right now.
Yeah.
Okay, so any questions, guys?
I don't know. It was a lot of info to take in like a solid 10-minute span. I don't know what to tell you. Tough scenes. So wait, you guys are doing a literary review, right? Like a research paper
Yes.
for this?
Yes, we're doing a literature review on what exactly, the AI does and how it does it.
Hmm.
And also we want to, find ways how the current process could be improved upon.
So have you guys found any like it's hard to say like real world examples, but like
Actually,
any, like,
so I
modern
actually
examples?
I did find a good example on this. So, a huge problem is, the consent of the consumer. Like that's, a huge problem. A lot of the tracking that happens, people get tracked across multiple websites from these cookies. So a good example of this I found was that Disney actually has something, the wristbands they wear.
Reason, like in the past, we don't know about that. I don't know if there's really any measures that are out there to prevent that from happening, other than local law enforcement and federal governments stop that. That's not really what we're researching. I think that that side of it is could be a downfall and a consequence.
Like repercussions of illegally using cryptocurrencies.
Yeah, but maybe there's a countermeasure that we don't know about.
Right, okay, that makes sense.
Do you have any more questions? All right, I think
Thank you, everyone.
Yeah, did we have anybody who wanted to be the next group to present?
Yeah, I'll go. Can y'all hear me well?
Perfectly.
Okay.
Yeah.
I'm at Valencia West right now, and I'm in a public space, so I'm just hoping that my internet is good enough. I'm currently tethering off my phone because their guest Wi-Fi sucks. So let's see. I'm going to share my screen. All right. And can y'all see my screen?
Yeah.
Okay. All right, so let me minimize this real quick. Okay. All right, so my research topic is the application of data distribution services and robotics communications middleware. As a brief introduction, we all have a semblance of an idea as to what robots are. but they are very complex cyber physical systems, and they consist of a physical frame, of course, actuators, manipulators, sensors, and computers. Examples of actuators would perhaps be motors. As for sensors, you would typically have either a LiDAR for detecting the environment, or you can have a stereoscopic depth camera. And you would also typically have IMUs, which are inertial measurement units, which are used to determine your orientation in space. And of course, you would have computers, computers being plural here. You can, of course, create robots with a single computer, but as they get more advanced, it is perhaps more advantageous to have multiple. And given this complexity, robotics middleware are necessary to simplify the software design. Such examples of robotics middleware would be the Robot Operating System, or ROS, which, as you can see in the bottom, it's not an operating system, it is a set of tools. So you would have the plumbing on the left-hand side, which shows the different connections that you would have in the communications background. You would have different tools such as RViz, which is a 3D visualizer. You would have different capabilities, and what's being demonstrated in this image is that it has tools for creating paths on occupancy grids. So you can have a robot that navigates an occupancy grid. And of course, you have a worldwide ecosystem with that's open source, and people contribute to that. ROS primarily provides hardware abstractions, device drivers, and above all, the communications aspect. And so to get into the communications, we should first acknowledge that there are two versions of ROS. There's ROS 1, and then there's ROS 2. So the problem that ROS 1 had was that it was plagued with a crucial bottleneck, and it consisted of a centralized broker that recorded the topic names and the TCP addresses that it would bind to. So if you look on the right-hand side over here, you have three blue ellipsoids. At the very top, there is a master, and that's the one that would keep track of the topics and their associated addresses. And then you'd have two other nodes over here. So the Hokuyo node on the left-hand side would advertise the scan topic at the address foo in port 1234. And then the viewer would want to subscribe to that topic. So it's subscribe to scan, and master would give it that address that the publisher Hokuyo gave to the master itself. And then the viewer would be able to connect to that Hokuyo directly. So the issue is that it all hinged upon this centralized master broker, which could cause problems, and it would only work for a single robot. It didn't work for multiple robots trying to communicate with one another. So this was fixed in ROS 2. They used the Object Management Group's Data Distribution Service, Real-Time Publish Subscribe. So it's OMG DDS RTPS. So what that would do is it would use a UDP broadcast as opposed to a straight TCP to provide a fast decentralized method of communication. It's fast because it avoids the overhead of TCP, which includes sequencing, guarantees of delivery, and retransmission of lost packets. And they provide guarantees of reliability by creating this application layer on top of UDP, which is the OMG DDS RTPS. So on the right-hand side, we have a little example infographic. So you have a publisher on the left, and then you have two subscribers on the right. So what would happen in an example of communication between these publishers and subscribers is you would have a send buffer from the publisher, and each subscriber would have a receive buffer and an app buffer. So it's important to note that in this specific example, it would have a heartbeat rate, which would be known by all of these devices. And that rate determines at which the sequences are terminated and continued. So we'll see that in just a second. So it gets the first bit of the sequence, S1. It goes from the send buffer over to the subscribers to their receive buffers, and it goes straight into the app buffer. It's in proper sequence, so it goes straight into the app buffer. S2 comes in, goes from the receive buffers straight into the app buffers. S3 comes in, goes from the receive buffers to their app buffers as well. And then because we have the heartbeat of 3 in this case, the subscribers would send ACKs for 1 through 3 back to the publisher. So it acknowledges that it received the sequence of 1 through 3. And then it would continue with our next sequence. So our next sequence, we have S4 that comes in and it goes straight to the app buffers. And then the issue comes in here. So we have the send buffer sending S5, but it is dropped. It is lost in the receive, and it's not in the receive buffer whatsoever on the subscription end. And then it would send S6. Those are not, S6 is not dropped. It's received by both. And as you notice, it also doesn't go to the app buffer because we haven't received the full sequence yet. So it would send ACK back saying that it received 4 and 6, but it's missing 5. So then the send buffer would send S5 again. S5 would be received, and then it would complete out the app buffer. So you'd have a complete sequence without losses. So then with the application in ROS 2, you have on the left-hand side, we have a graphic. It shows on the very bottom down here, it shows RTI Connext, Prism Tech, OpenSplice, Twin Oaks. They use something called eProsima FastDDS, I believe. So these are different DDS libraries that can be used. You can use any different one. And then it has an abstraction layer built on top of that. So you can use any of these different libraries. It has a ROS client library, and then you have your user land code. That's where you create your own robotics apps. On the right-hand side, it demonstrates the manner in which messages are encoded and serialized and sent over that network. So you would have a ros.msg file, for example, and it would generate a C++ class. So it would generate a header file and a source file, and you could use that in your software. You can use that when you're building your app. And it needs to translate it over to this interface description language, the DDS IDL. That's necessary in order to have it interface properly with the DDS specification. So on the bottom, we have a little example of an SRV file. So SRV and MSG files are very similar. The only difference is that MSG only contains different data types, whereas the SRV contains a request on the top and a reply on the bottom. The 3 dashes there designate where the request stops and the reply begins. So in this example, it's just a simple summation. So it would take in 2 numbers, A and B, and then it would reply with the sum of the 2. So you just do A plus B and store that in sum and send that back. Here's a visualization of Gazebo. This is one of the tools that ROS provides. It's a simulator for robotics. So what you got here is multiple drones. So instead of just having a single complicated robot, you can also have multiple different robots that are independent of one another, communicate with one another. And you can have these complex drone swarms and all sorts of different robots communicating with each other, assuming they're within the same network. So solution 2, instead of relying on UDP exclusively, we would do an intermix of UDP and TCP. In this case, I'm proposing that I use Zyre and ZeroMQ. These are 2 libraries from the ZeroMQ community. So Zyre provides group messaging over LANs. Peers can join and leave as they please. They can communicate without any central broker, so there's no master server involved, and they can talk directly to each other through what is called a whisper, or they can talk to a group, which is called a shout. ZeroMQ, Zyre is built directly on top of ZeroMQ. It's a messaging framework, and you can communicate through InProc, inter-process communication, which is IPC. You can do TCP, or you can do UDP. And it also provides a multitude of different messaging patterns, such as pub/sub, request/reply, router/dealer, push/pull, and pair/pair. Pair/pair would be used when you're doing pipe communication, for example, between different processes. And so this is just a simple illustration. So Zyre would be used for UDP to broadcast the topics and the bound addresses. So you would join, you would shout that to the group, and the the group would shout back to you what topics and bound addresses they have as well. And then you would use ZeroMQ to create the publish, subscribe, and request reply pattern. So the publish subscribe is very simple. So it's analogous to having like a weather broadcast. So you're saying what the temperature is, and you have all these different people listening to that broadcast. Request reply would be used for services. So you would make a service request and you would get a response back from that specific address. So as you can see on the right-hand side, you have a client and a server. Sequence 1, you have a length of 669, and then it would acknowledge with 670. So it knows that it got all those bytes. And then the next bit of the sequence would be 670, and the length would be 1460. It would acknowledge with the sum of those two, 2130. So it's just a constant back and forth with the lengths and the sequence numbers. So basically it comes down to the OMG, DDS, RTPS, reinventing the wheel. These things already existed in the layer with TCP. They didn't necessarily need to recreate an application layer for this to use exclusively with UDP. And so this is my proposal also. Instead of using encoding the messages the way ROS would do, ROS would create XML representation. So it's called XML RPC, so remote procedure call. Instead of using XML, I would use Google's protobuf. And as you can see in the upper right-hand corner, it has different message sizes. So there's a JSON encoding, flat buffers, a protobuf. Protobuf is much smaller than any of those other two, as well as XML for that matter. So this is an example in the center at the top. It shows what the protobuf format looks like. So you would have the same add request reply situation. So you'd have your add request, which consists of A and B, and then your response would consist of the sum, which you would just assign to the sum of those two. And it would also, exactly like ROS, would generate a C++ class for you to use, and you can serialize that data and then send it over the wire. Timeline, so this is the first week here, so I've been researching current DDS implementations. 2 to 4, I port Zyre from C to C++ because it's based on CZMQ, and I need to use CPP-ZMQ. Week 5 to 6, compose and present findings. Here are my references, and I believe that's it. So I'm open to questions if anybody has any questions.
Yeah, so I have a question.
Yeah.
Related on the beginning of the slides, when you mentioned ROS, the robot operating system, is that like the same as the desktop computers, like the OS that we have, where you have like a kernel mode and then the
No, it is not. So that's the thing. It's not an operating system. It's a terrible name in my opinion. It's a robotics middleware. It's just software that sits on. I run it on Ubuntu, for example, but they also have they've compiled it on Windows, and I believe they've compiled it on Mac as well.
Okay, thanks.
You're welcome.
I have a question.
Yeah.
What's can you go to solution 1 and then solution 2?
Right here?
This problem. Yeah. So what are the pros in in the comparison to solution 2? What's the benefit with solution 1 compared to solution 2? Which one's better? What are the pros and cons?
I suppose that's really what my research is supposed to be on, is trying to figure out which one would be more efficient of the two. My point was acknowledging the fact that the first solution, so it's OMG, DDS, RTPS, it uses UDP exclusively. And so the issue was highlighting that UDP by itself doesn't have any promises of sequencing or guarantee of delivery of messages. So they created this protocol, which is in the application layer. So it's on top of everything else. So it's effectively just a specification for a library and whatever programming language you choose. And it provides those guarantees through the software, whereas TCP has those guarantees built into the actual specification of TCP. So it guarantees that those messages get to where they need to be. So that's what I'm trying to figure out is I'm going to use UDP to broadcast and not have the centralized broker as shown in this image here. I will use the UDP to communicate the different topics to all the different nodes in the system. But I anticipate using TCP to have direct connections between the publisher and the subscriber and the different services. So similar to how it shows the Hokuyo and the viewer at the bottom in this image, they would connect to one another. There is a connection, whereas with UDP, there is no connection whatsoever. It's a connectionless protocol.
Okay. Thank you.
You're welcome. Any more questions?
I had a question. Relatively, how much faster is the protobuf from the XML format?
I'm sorry, could you repeat that, please?
How much faster is the protobuf from the other, I guess, the next leading format?
I would have to do tests specifically on their implementation. I would like to talk to, so Dr. Farangi, he's a member of the RTIS lab, so that's the Real-Time Intelligent Systems Lab, and they work pretty much on this sort of stuff. And they have some students going to a conference in San Francisco here in the next week or two, I believe. And they work directly with ROS too. So I'm going to try to get into contact with them so I can actually measure the different, well, it's a matter of speed and size. So the image, the graphic here I've shown shows the different size of the serialized data using JSON, flat buffers, and protobufs. I wouldn't assume that it's much larger than the flat buffer, but I don't have the concrete numbers for that matter. But the protobuf, the advantage is that it's not a non-proprietary format that Google has put a lot of work into, and they've put a lot of work into making it smaller and faster to serialize the data, which makes it more efficient for networking purposes for that matter.
Thank you.
Any other questions? Okay, I'll stop my share and then we can move on to the next person.
Do you have anybody else who wanted to volunteer to go next?
I think we might be up next, or Kyle. You.
Yeah, I think, are we all that's left? I think it's just my group.
Yeah, we can go.
All right, cool.
All right. Let me just share.
Yeah, okay.
All right. Okay. Are you able to see my screen?
Yep.
Let me go. All right.
I see y'all ready. So me, Jalen, Lewis, and Kyle, we're working on the applications for GSM networks, and we are networks with an attitude.
Oh, what's going on?
All right, yeah, so like I said, my name's Kyle, and I just want to give a quick introduction of what GSM is. So GSM stands for Global System for Mobile Communications. It was developed in the early 80s and it was starting to be implemented in the 90s. So this was the, basically this was the protocol that started 2G mobile networks. So we started with that all the way back then, and over time, we've kind of used it as a base to evolve our mobile networks. So for example, like newer 5G mobile networks, they're using a like iteration of GSM called a GSM-A. So the majority of carriers that have 5G are actually using GSM. So Basically, it's a hardware-based solution. So each device has a SIM card to identify itself, and that's how it's able to connect with the networks. And it's made up of a few just kind of basic components. So the mobile device itself, the base station subsystem, network switching subsystem, and the operation and support subsystem, which is more of kind of a outside support system. Okay, next slide. So how it's currently used is mainly for mobile devices. So, I mean, everyone here has a smartphone. So we all know that when we're not connected to Wi-Fi, we use some cellular data to connect to the internet, send messages, anything over the internet or wirelessly, we do through cellular data. So this is done using our carriers' networks, which all use the GSM protocol.
All right, so unfortunately, like most technologies developed, it comes with their respective shortcomings. One of them being interference. Now, how does that happen? So in order for GSM communication to work, it uses a combination of two access schemes. One is TDMA, which is time division multiple access, and FDMA, frequency division multiple access. So to put this into perspective, let's just think about the United States, which has a bandwidth of around 900 megahertz. Yes, it has a bandwidth around that number. So what GSM actually does is they just take that bandwidth and they just divide it into multiple sub-carrier divisions on the frequencies. And then that subdivided frequency, they allot it to specific time slots. That's using the TDMA scheme. And because of these two combinations, that divided frequency, multiple users sharing that same bandwidth. And of course, the higher the number of users under the same bandwidth is going to increase that interference. Now, an interesting note is one solution for this interference problem is based on frequency planning or frequency hopping. What this is like algorithm, it's like a frequency algorithm such that these interferences can be reduced. A really interesting algorithm is called the ant colony optimization algorithm, which, just like the name suggests, it uses the behavior of ant colonies such that this frequencies path can be allotted to a more efficient way such that we can reduce this interference. Now, another shortcoming regarding this current GSM involves the internet access on rural areas alongside maintaining the high quality network in these places. One of the primary reasons of these two bullet points here is because private telecom service providers, they don't see these villages as a viable commercially a place. So one way or one solution to at least provide such expansion is to is to apply the transmission techniques such that reliability and cost effectiveness is increased. And of course, when we have a network where multiple users are interacting with each other, security is a big issue. So issues such as stealing information or spamming, use of baits so that information can be stolen, or viruses that damages such devices, they all pertain to the same security issues.
All right, so this is some of our kind of objectives that we want to achieve by the end of our research. So we want to kind of really go into depth of how GSM technology was created and how it's been improved over the years, and how it's has had its advantages and disadvantages over other protocols such as CDMA. We're also wanting to expand the use of GSM. So like I said, its main use case is for mobile networks, mainly phones. So we want to do research into seeing how we can expand that and use the technology we already have to do even greater and bigger things.
All right, so another objective that we're trying to learn is the different architectures available that provides internet connectivity over longer distances, even farther than urban, high populated places.
And with the demand of electrical energy being increased over the years, we want to look for ways to improve the daily lives of people and reduce the electrical energy consumption that you use on a daily basis. So what I'll be focusing on for the project is a GSM-based smart electric energy meter billing system, which will help lower the cost on electricity that people use. And how the system works is it will ping the user when they are overusing their electricity, or when they're it'll be similar to, like, say on Instagram, how it logs your daily use, or how YouTube will do the same. And it will send an SMS message to your phone, and it'll give you details on how much electricity you're using. And this will help users because they can, like, plan how they use their electricity, and, you know, get lower costs for their monthly payments and whatnot. And this system's good because it's economical and it's rather low cost.
So my area of focus is on the expansion of GSM, specifically on rural areas. I will be discussing about possible techniques alongside architectures that perform such tasks so that we can increase reliability and cost effectiveness. Some of these approaches include splitting the splitting of the baseband unit and the remote radio unit. And this splitting can be possible with a modification on the GSM transmission relative to Wi-Fi.
Right, and like I said previously, with the expansion of GSM and trying to use it in different use cases other than mobile networks, I saw and I wanted to kind of focus on how we can integrate GSM networks into smaller sub-networks. So we could have, for example, like GSM smart homes or smart cities. So we already have a kind of base. We kind of have a base for, say, like smart homes. We have devices that connect to each other in our homes and all around, and it's all in this kind of loosely integrated network. What I would be focusing on is how we could use GSM and cellular technology to actually increase that integration. So you could have smart cities, for example. I saw a research article on having garbage collection, have that be automated and done, and all the communication is done through GSM networks. So all of the data can be tracked, and all of the automation that needs to be done can be done through GSM networks, either through SMS, pinging, any data that's transferred through, and how this can be improved upon as we also improve our data speeds using GSM.
So for our schedule towards the final week, for the first 2 weeks, we're just going to be working on research material. So until next week, we'll be like researching our final stuff. And from weeks 3 to 4, we'll start working on our paperwork and research, and well, not research, but the first draft. And for week 5, we'll finish our paper, and then we'll start working on the presentation. And by week 6, we'll have the presentation done, and we'll start practicing, rehearsing for the final week, which we will present and submit our final report.
So overall, having explained the usage, the shortcomings, possible solutions, and improvements, enhances our drive to explore the application of GSM networks. or more like GSM to be used as a network of networks. Research papers and published documents are extensively used in order to improve everyone's understanding in the potential of GSM, again, to be used as networks of networks. These are references. Any questions?
Yeah, actually, here I have one for you. Did y'all touch on like the overall throughput of GSM networks? Like
we didn't go into detail here since it was just our proposal, but we'll definitely be looking into the throughput, latency, and how that's being improved over time, and how we can look into different technologies to that prove that further, and that would inherently be, you know, a positive thing for the things we are researching.
Got you. Thank you very much.
No other questions?
I guess I'll just stop sharing.
All right, thank you guys.
Thank you.
All right, I think that my group is the last to go, right? That's it.
I think so. Yeah.
All right. Yeah. Screen share in a second. All right, so present. Check. Can you guys see the thing?
Yes.
All right, perfect. So my group, my name is Dimitri, and my group, we did our research proposal on BAW filters, and ultimately we're going to be going into their impact on the 5G networks. With how hustle and bustle society is going nowadays, we extremely need fast internet, fast speeds. With 4K and 8K streaming on the rise, we are going to need higher quality data to be able to come through, and we're going to need filters such as like the BAW filter or the SAW filter, which I'm going to talk about, to get that information from point A to point B reliably. Some of the other problems is the lack of stability from the 5G towers, how these filters impact the battery performance, and with the advancement of the Internet of Things, like you just need more data, or you need quality data. Why we had chosen to talk about BAW filters is because they have been semi-recently into development. Now they've been coming out with new technologies, but before that was the SAW filters, which are surface acoustic wave filters that have been used since the mobile phone era, like the beginning of it. These filters, they have high electrostatic discharge rates, which cause interference that the BAW filters don't have. BAW filters allow for higher frequency communication, so data to be transmitted a lot faster within the, I believe, like 2 gigahertz to like 7 gigahertz range. And ultimately, the BAW filters are they're slightly more expensive, but they help bridge the gap between like fast and reliable data with the SAW filters. How they essentially work is the signal propagates through the filter. For the BAW filters, it goes vertically and it goes downwards into the filter. The thickness of the BAW filter kind of helps with with mitigating the interference that can be caused from like the resonators inside, like the resonations inside. And then with the SAW filters, it goes horizontally across the multiple layers of metal. Yeah.
So how is a BAW filter made? So when you see that figure on the right, you're looking at the acoustic model of a BAW filter. This especially represents the SMR, which if you go to the next slide, it shows it the same way. Yeah. Yeah. So essentially it's 2 electrodes that sandwich a piezoelectric film, and underneath it are Bragg reflectors. So can you go up or back? So yeah, so the most common material is used for the piezoelectric film is aluminum nitride. So how it works is that the acoustic wave comes in, and to preserve that wave or signal, you use the Bragg filters to reflect, or Bragg reflectors to reflect that, and you essentially want very you want to minimize the leakage of the acoustic wave. So then the manufacturing process. So these filters are on wafers, and there's probers that go and probe the die one by one, which and these and all these go into lots. And so essentially, when in the process of that, many things can go wrong. There's certain parameters that these probers look for, especially quality factor and the coupling coefficient. So the quality factor basically just means that it's like the ratio of the initial energy stored. And yeah, you can think of it as like, so if you have a very low quality factor, you can, your oscillation pretty much dies out rapidly. Whereas if you have a high quality factor, your oscillation doesn't die out as fast. You can think of it as like a sine wave not dissipating, or yeah. Anyways, can you go to the next slide, Dimitri? Oh, yeah. So yeah. So current works on BAW filters. Right now, the most recent technology is micro BAW, SMR, like the one I talked before. The older generation is FBAR, which stands for thin film bulk acoustic resonator. Instead of the Bragg reflector, it has an air gap. Bragg reflectors are more efficient. So another current work is, which industry is trying to improve, is thinning the layers and minimizing insertion loss. By minimizing layers, you essentially limit the resonator coupling, and thinning the resonator coupling just means that what is it? It's inversely proportional to the frequency response. So yeah. And to minimize insertion loss, right now, industry usually, or insertion loss is pretty much the loss that relates to like the power signal, the loss of the power signal. And right now, currently in our phones, the loss is less than 1 dB. So that's pretty good. And yeah, on that figure, you can see the passband, the frequencies you want to filter out, and how much power loss goes through that, and it's pretty minimal, but there's still ways to improve. So yeah. Caleb.
Right, thank you, Sebastian. Good afternoon, everyone. The final part of our proposal will be about outcomes of BAW filters and 5G networks. That being said, everything that has been mentioned in the current work of BAW filters will have an outcome. There are 3 types of outcomes I'll be talking about. The first one is transmission insertion loss, reactive insertion loss, and finally the implementation of BAW filter in the industry. For the transmission insertion loss, nowadays we have phones that last for a long time during talking because of BAW filters. Antennas actually have become more powerful by using BAW transmit filters, which are used between the power amplifier and the antenna cell phones application. We also have better thermal performance. The self-heating due to power dissipation, the filters lead to no uniform frequency shifts of the insertion loss. Second part of outcomes, the BAW filters keep RF interface out, which cause better signals. It's also evolving to support higher frequencies and increase bandwidth for the new 5G and the Wi-Fi. That's also actually improved the receiver signal power. Final outcomes. Final outcome, I'm going to discuss how BAW filters are implemented in the industry by discussing 2 examples. The first example is the mobility. For example, the use of these filters in application like smartphones or tablets. For non-mobility, we have examples like Wi-Fi, hotspots, and Bluetooth. This application actually have significantly increased. Next slide, please. In conclusion, we have gone over 3 main topics: motivation, current work, and outcomes. The takeaway from our proposal are the importance of BAW filters in today's technology, as we have mentioned during this proposal. We also mentioned the coursework that are applicable right now in the industry. Finally, we give some good examples of using it. There are questions like we would like to keep open for everyone until we present the future of BAW filter. We know that any technology lasts for at least 25 years before becoming open to everyone. So we are looking that these BAW filters still have many years in the industry. And finally, will these filters be using during next generation of networks? Thank you, everyone. If you have any question, we will be more happy to answer. Also, we have a schedule right here. This is our schedule for coming weeks. We have a resource material for the week 1 and 2. Week 3 and 4, we'll do like a rough drafts. Week 5, 6, we'll be working on presentation, and the final week we'll be presenting. Next slides will be about the references that we use. They are available here for everyone. Thank you, and if you have any questions, we'll be more happy to answer these questions.
Yeah. Is this something you're working on, Sebastian? I seen you have the lanyard around your neck that says Qorvo on it, and one of the images was also from Qorvo.
Yeah. I work with these filters.
Gotcha. And I also wanted to know what exactly is the effect of having the piezo electric material in the filter?
So the piezoelectric film basically it acts as a resonator. So essentially, it preserves incoming acoustic waves, and well. So for the filter, there's different topologies. So it's like the designers basically they basically combine elements to meet certain parameters for like it depends on the specification, like whatever the customer wants. But say you want to you want a band between I don't know, 500 megahertz to 600 megahertz, and you want a low insertion loss. You want a low insertion loss, like less than 1 dB. Like these are wait, go back to your question. Sorry, I got a little off track.
No, I mean, that's actually a good answer. So you can vary the different materials to target different parameters for your devices.
Not very. There's trimming. There's trimming of the layers to that. The material stays the same for the most part.
Perfect. Thank you so much.
So between the SAW and the BAW filters, which one's more expensive or efficient, or yeah, which one's like easier to manufacture?
SAW is easier to manufacture, but it's less efficient over like a wide range of temperatures, and it doesn't handle as high frequencies.
All right, thank you.
Mm-hmm.
So would kind of the end goal be to put BAW filters in like all, say, cell towers, or do the majority of cell towers already have like SAW filters or some sort of BAW filters, but you guys would like expand that and have every cell tower to have a BAW filter?
BAW filters are used mainly in mobile devices and like non-mobile device. I guess a non-mobile device could be like a router or switch it, or I don't know if switch. Yeah, I think of it as a router. Yeah, or like Bluetooth. I don't think it's used in cell towers. Maybe.
Okay, so they're not needed literally every step of the way for mobile connections.
For mobile connections, they are. Yeah.
Okay, cool. Thanks.
Yeah.
Sorry, it sounds like it's fine.
What, Dimitri?
What you said?
You cut out. Do you guys have any more questions, or are we done?
I think we're done. Do y'all just need to talk to the professor, or should we just dip?
I'll
I have no idea.
I'm just gonna stop recording.